Hello there. When we think about sorting data, our minds almost always jump to one thing, comparing items. Is this bigger than that? Is this one before that one? But what if I told you there are some wonderfully clever methods that can sort a list without making a single comparison? That's what we're exploring today.
Just let that idea sink in for a moment. Most sorting algorithms you've likely encountered, things like merge sort or quick sort, well, they live and breathe by comparing elements. It's their fundamental operation. But today, we're going to sidestep that entire process. How is that even possible?
Well, it turns out you absolutely can, but only under very specific conditions. These methods are what we call specialist algorithms. They aren't your all-purpose sorting tools, but for the right kind of data, they are astonishingly fast. Think of them as clever shortcuts. Our first specialist technique is called counting sort. I rather like to call it the tally trick, and you'll see why in just a moment. It's a bit like a secret weapon, perfect for a very particular kind of sorting problem.
Now, the formal definition can sound a touch academic, but the idea behind it is beautifully simple. Instead of asking, is this number bigger than that one, we're just going to ask, how many of each number do we have? We're not comparing, we're just counting.
Right. Let's get our hands dirty and see how this actually works. Here's a small, jumbled array of integers. Our job is to get them in order. But remember the main rule: no direct comparisons between any two numbers. So where do we begin?
Step 1 is the tally. We create what's called a count array to act as our frequency table. We simply go through our original list and tally up how many times we see each number. We find 1 1, so we note that down. We see 2 2s, so we make a note of that. 2 3s, and so on. It's exactly like counting votes in an election, isn't it?
And now for the final step, which is just as straightforward. We use our count table to rebuild the array from scratch. The table tells us we have 1 1, so we place a 1 in our new array. It says we have 2 2s, so in go 2 2. We just keep doing this for each value, and before you know it, we've built a new array that is perfectly sorted.
And this is the crucial takeaway. We have a sorted list, but at no point did we ever ask a question like, is 4 greater than 2? The entire process was driven by counting frequencies and then reconstructing the list based on those counts. It's a completely different way of thinking about sorting.
But, and this is a very important but, this clever trick has a major limitation. It's only really effective when the range of the numbers, which we call k, is reasonably small. Imagine if your array contained just 2 numbers, 2 and say 10 million. To use counting sort, you would need to create a count array with 10 million empty slots. That would be incredibly wasteful.
Okay, on to our next specialist tool, bucket sort. If counting sort was a tallying exercise, I want you to think of this one more like a distribution game. It's designed to excel with a completely different type of data.
The idea here is really quite intuitive. You start by setting up a series of empty containers, or buckets. Then you simply go through your list of items and place each one into a specific bucket based on its value. It reminds me of a postman sorting letters into different slots for each street on his route. Now, bucket sort truly shines when dealing with data that's spread out fairly evenly, what we call uniformly distributed. It's especially good for decimals between 0 and 1, so let's try it out with this array here.
First up, we create our buckets. Let's use 5 of them. The rule for placing an item is simple. Multiply its value by the number of buckets. So for 0.17, that's 0.17 times 5, which gives us 0.85. We just look at the integer part, which is 0, so it goes into bucket 0. For 0.26, that's 0.26 times 5, which is 1.3, so it goes into bucket 1. We do this for all the numbers. You'll notice bucket 4 ends up with 2 values, while poor bucket 3 is empty. That's perfectly all right.
So the whole process breaks down into 3 simple steps. First, we distribute the numbers into the buckets. Second, and this is a key step, we sort the numbers inside each individual bucket. Now this is where you might use a standard comparison sort, but on much smaller, more manageable lists. Finally, you just combine or concatenate all the sorted buckets back together in order.
And voila! After we sort the items within bucket 4 and then stitch all the buckets together from 0 up to 4, we get our final, perfectly sorted list. You see, the heavy lifting was in the distribution, not in that endless cycle of comparing every single element with every other element.
So there you have it. 2 powerful but, as we've seen, highly specialized sorting techniques. The most important lesson here isn't just how they work, but when to use them. These are not one-size-fits-all solutions. Knowing which specialist tool to pick for the job, well, that's the mark of a thoughtful programmer.
So here is a little cheat sheet for you.
Counting sort is your go-to for integers within a small range, that k value we talked about. Bucket sort is the champion for uniformly distributed decimals. When you use them correctly, they can achieve what's called linear time complexity, or ON plus k. In simple terms, this means their speed is tied to the number of items and the range of items, which is often much faster than a comparison sort's O of n log n.
So, the next time you're faced with a sorting problem, just pause for a second. Before you reach for that default sorting function, take a proper look at your data. Is it a list of integers in a tight range? Is it a set of evenly spread out decimals? You now have two new, very sharp tools in your toolkit. The only question left is, which one does the job demand?